Let's summarize. We talked through 1D version of EM, and in both of our examples, we looked at real-valued data, where you use Gaussians. If you had discrete data, data like text, you would not want to use Gaussians. You would want to use different distributions. So you would want to use multinomials, and there are variants of these mixture model algorithms that look that use multinomial distribution. So PLSI, for example, is quite popular for modeling text. It's a probabilistic method. It has a specific objective function. It's trying to maximize the likelihood of your data. It's quite similar to k-means, really. So if you think about the procedure that we used, there is a lot of parallels between Gaussian mixture models and k-means. There are, and the similarities also extend to the properties of the algorithm. So it is going to be sensitive to a starting point. So depending on where you place those Gaussians, you will end up with a different quality of the fit later. So if you wanted to have the best fit for 10 Gaussians, you would run it multiple times with different initializations and then look at which one of the random restarts gave you the highest likelihood of the data. It has the same problem with converging to a local maximum. How do you measure convergence? It's a little more difficult than with k-means. With k-means, there will come a point where no points will change cluster assignment. Here, it doesn't happen. Those probabilities are going to keep drifting slowly. But what you typically do is you impose an epsilon on the likelihood, and when the change in likelihood is smaller than the epsilon, you just stop. Or you run it for a fixed number of iterations. And just like k-means, you can't use it to discover k. The likelihood will usually keep growing as you throw more components into it. So what's different? How is this different from k-means? The biggest difference is hard versus soft boundaries. In k-means, a point is assigned to one cluster or the other. Here, the point is assigned to all of the components, just with different weights, with different posteriors. And another really big difference between k-means and mixture models is the role that covariance plays in the algorithm. So if you remove covariance, Gaussian mixtures and k-means are going to look really, really similar. Because remember, in a Gaussian, all you're doing is, what the Gaussian computes is it basically looks at how far the point is from the mean, the squared distance, and then it raises e to that power, which is sort of inconsequential. So it's really just computing Euclidean distance, which is the same thing that k-means was computing. One thing that makes Gaussian mixtures very different is the covariance, because what the covariance does, it changes the shape of the Gaussian, right? So if you have two variables, it can take a spherical Gaussian and sort of extend it in one dimension. And what that means is that distances on the y-axis are a lot more important than distances on the x-axis. K-means cannot do that. K-means treats distances on all axes equally. And the mixture model, through the covariance, can make some distances, some attributes, a lot more important than others when you're measuring distances. And not to mention that it has this notion of covariance, so it can meaningfully compare data when the attributes have heavy correlations in them, which k-means cannot.